So far this year, all the chemical reactions we've looked at have been one-step chemical reactions where they've gone from, two or three or maybe one product into, one or two or three or however many reactants. But it is possible for chemical reactions to be multi-step. For example, let's look at a one-step reaction and then what that would look like if it would break up in three steps. So the one-step reaction is shown here between C2H6 and oxygen gas, and it's going to produce carbon dioxide and water. So 2C2H6 plus 7O2 yields 4CO2 plus 3H2O. So just notice that we started off with C2H6 and O2. We ended up with CO2 and H2O. And so this same reaction could be done in three steps. And so in three steps it would look like this. We started with C2H6. So here we start with C2H6. It decomposes into C2H4 and hydrogen gas. Okay. Now notice though that C2H4 and hydrogen gas are nowhere in this original problem. And so that means that we're going to have to end up using them up in the other two reactions so that we end up with our products, because this reaction didn't produce either the CO2 or the H2O. So one of the ones that sort of we're not going to end up with is that C2H4. Notice in the next reaction we have C2H4. It's being reacted with oxygen gas, and oxygen is something we started with. So some of that oxygen we start with is going to be right there. And when we react with those two, we end up with CO2 and H2O, which are exactly the two things that we want here. Now the problem is that that very first reaction produced water, right? And so because it produced, or it's not water, it produced hydrogen gas. Because it produced hydrogen gas here, and that's not one of the products here, we've got to get rid of it somehow. And so the way it says to get rid of it is this third step in the reaction. So 2H2 plus O2 yields H2O, and so that will react out all of our hydrogen that's here. And so notice that what's ended up happening is that the only things now left are going to be CO2, H2O, and H2O, and sure enough we end up with CO2 and H2O. So note that, as we said, both reactions result in the same two products, so CO2 and H2O. It's just the three-step reaction produces two intermediate products, which are the C2H4 and the H2. That it produces them to start with, they end up getting used up later on, and then in the later steps, but we still end up with the same two things whenever we're done. And so this oftentimes happens. In fact, many chemical reactions are in reality multi-step reactions, even though we treat them oftentimes like they're one step. But the fact that we can basically take a reaction and it looks like it's one step and write it in terms of several other steps ends up being really, really useful in terms of understanding the way that heat is released in chemical reactions and absorbed. So let's take a look at that. So when we are comparing single-step and multi-step reactions in terms of the energy released, we can apply something called Hess's law. So Hess's law says that the enthalpy change for a reaction is the same regardless whether it occurs by one step or by multiple steps. And so that if we have a one-step reaction and the enthalpy change is negative 500 kilojoules per mole, and that reaction could also be done through 7 steps, 7 different reactions, that the enthalpy change would also be the same thing it was before. If it was negative 700 kilojoules per mole to start with, now it's still going to be negative 700 kilojoules per mole. It doesn't matter whether you go through one step or go through multiple steps. The enthalpy change for the reaction is exactly the same. And so one other way of putting this is that if you know delta H naught for the individual steps in a multi-step reaction, you could figure out delta H naught for the single-step reaction. And this is really helpful in cases where you can't do calorimetry, it's not available to you, or you need to calculate it to check and see if the calorimetry gives you the right results. This is a way of calculating delta H naught as opposed to simply just measuring it like we can do with calorimetry. So calorimetry is the experimental method. This is the theoretical method. This is the way that we can figure this out if we can't do an experiment on it. So the key to applying Hess's law is to add up the products and reactants of each of the multi-step reactions in a particular manner so that it produces the single-step reaction. You can't necessarily just add together all the single steps willy-nilly. You've got to figure out the direction the reaction goes. You have to figure out the proportions the reactions are in. But if you can basically add the reactions up in a way so that it gives you the same result as the original amounts, and it gives the same amounts as the products that are in the single-step reaction, once you add up all the multi-step reactions, then once you've done that, you can add the enthalpies of reaction for each of the steps to get the enthalpy of reaction for the single-step reaction. So let's look at an example. We have a single step reaction, which is the same one that we saw before here. The 2C2H6 plus 7O2 yields 4CO2 plus 6H2O. Ends up with a total enthalpy change of negative 3120.8. And our goal is going to be to show that whenever we add up these multi-step equations using Hess's law in order to get the single step, that we're going to end up with the same value for delta H. Now, so first thing, let's just take a look. So we start off with 2C2H6 in our original equation. And looking at our multi-step one, we can see that C2H6 really only shows up one spot, shows up in step 1. So we're going to start off by writing that one out here. So we're going to say we start off with C2H6 yields C2H4 plus H2. Now, does this give us the C2H6 we start with? Sort of. It gives us C2H6, but if you look very carefully at this first one, you'll see it's not just C2H6, it's 2C2H6. Well, there's not another C2H6 that shows up here. And so in order to make it so that this first step in our multi-step equation has the same number of C2H6s, we're going to have to basically multiply all of our products and all of our reactants in this equation by 2. And so we're going to put a 2 out front here. We're going to put a 2 out front here. We're going to put a 2 out front there. It's not reduced now, right? This reaction is not fully reduced. But by Hess's law, we've got to do this to make sure that we can figure out how many of each one's needed for the 3-step reaction, because we can't really balance a 3-step reaction in the way we balance a traditional reaction. We've got to basically balance them this way to make sure we have the same number in our multi-step reaction as we do in our original single-step reaction. Now, here's the thing, though. Once we put those 2's out there, we have changed this reaction. It is no longer C2H6 plus yields C2H4 plus H2. And the delta H for this is based on it being without the 2's. So we have to remember back to what we said about what happens to your delta H naught whenever you modify the equation. What we said is that if you end up multiplying the equation by something, by 2 or 3 or 4 or whatever like that, then you also multiply delta H by that same amount, by 2 or 3 or 4. And so if we're writing out our delta H, we're going to say our delta H naught is going to be now not just 136.2, but 136.2 times 2. And so that's going to give us our new value here because of the fact that we had to multiply these guys out. All right, so that's going to be our first step here. So the next thing that we see in terms of doing this is we've got to figure out how exactly are we going to sort of get rid of our next thing here. So we got C2H6, that's where it needs to be. But this produces C2H4, and we really don't want to have C2H4. That's not one of our products in the original one here. And so to cancel out the C2H4, we're going to have, since the C2H4 is on the reactant side, or sorry, on the product side of the original one, we're going to want to react it. And so that means we need to get a C2H4 from one of the other 2 steps onto the left side, onto the reactant side, so we can react it into something else. And so do we see C2H4 in either one of the other 2? In fact, there it is in step 2 right there, C2H4 plus 3O2. Now, one of the problems we run into is that just like we had previously, now on this one we have 2 C2H4, but this one's just 1 C2H4. So we're going to have to multiply it by 2 the same way we did the last one. And so we're going to go ahead and start writing this down. So we have on our next step, that should be a C, C2H4 plus 3O2, but technically we don't want to put a 3 out there because we said we're going to double it, right? So we're going to put a 2 out here. That now instead of being 3O2, it's going to be 6O2 because we've doubled everything, so that 3 becomes a 6. So 6O2 yields, instead of 2H2O, I was going to write out the whole thing here, might as well, and then I'll put the numbers in later. So CO2 plus H2O, and so just to make sure I got our colors matched up here, so instead of being 2, this is now going to be 4. Instead of being 2, this is now going to be 4. Now, we had before that delta H is 1410.8 kilojoules, but because we multiplied this by 2, it means whenever we do this, we're going to get delta H naught is going to be twice that, negative 2821.6 for our delta H naught for that one, because we took this original value, multiplied it by 2 because we multiplied the second step by 2. Now let's see if anything's canceled here. So we originally said C2H6 yields C2H4 plus H2, and we have 2 C2H4 over here, but down here we reacted away that C2H4, so we can cancel this out. We can cancel this out. They're now gone in this reaction. So at this point, if we were actually to finish this at this point, which we can't, we would have left over on the reactant side, we'd have C2H6 plus 6O2 yields 2H2 plus CO2 plus H2O, 4CO2 plus 4H2O. But we're not done yet because that's not the reaction we want. So our next step is, let's take a look at this H2. We have an H2 on the product side we don't want. There's no H2 over here. And so to get rid of it, we want to say, well, which one of our equations has an H2 that we can get rid of? Well, step 3, the only one we haven't used, starts off with 2H2 plus O2. So we want to get rid of 2H2, and sure enough, this has 2H2, so we don't need to multiply anything by 2. We just need to write out that equation. So we have 2H2 plus O2 yields 2H2O. All right, so now that we have that, that's the third step, and we have all 3 of our steps here. Step 1, step 2, step 3. And let's see what this cancels out. So we have 2H2 down here, canceled out this 2H2 right here. And let's see, what else do we have? Well, I don't think anything else cancels. On the reactant side, we have our C2H6, or 2C2H6. We have 6H2O. We have an O2. On the product side, we have CO2, H2O, and H2O. So that means reactant C2H6 and O2, C2H6 and O2. On the product side, CO2 and H2O twice, CO2 and H2O. Let's see if adding these up gives us the right amount. So let's add all these guys up. So on the reactant side, we currently have 2 C2H6 plus, we have a 6O2 plus another O2. So 6O2 plus O2 just gives us 7O2. Yields, on the right side, we have 4CO2 plus, we have some extra waters. We have 4H2O plus 2H2O, which would be 6H2O. And so let's see, how does this match up? 2C2H6 plus 7O2, 2C2H6 plus 7O2 yields 4CO2 plus 6H2O yields 4CO2 plus 6H2O. We have the right equation. So we've managed to write out these 3 reactions to equal out to that original one-step reaction. But let's look back at that enthalpy change. So at the very end, we already said that first one ends up being 136.2 times 2. The second one, we already multiplied it by 2, so we got the negative 2821. Now the third one we didn't write down, but let's write that down here. We didn't change this last reaction, right? We didn't multiply it by anything. So that means delta H should just be equal to negative 571.6. And so last step, Hess's law says that the enthalpy change for multi-step reactions is the same as the enthalpy change for a one-step reaction, as long as they end up and start at the same things. So let's try adding these up and seeing, we add up all our enthalpy changes here and see what it adds to. So 136.2 times 2 is going to be what? 272.4? If I'm doing that in my head right. So 136.2 times 2 is 272.4, and then minus 2821.6. And then we're going to add or subtract off another 571.6 minus 571.6, and whenever we do that, I get negative 3120.8. So delta H naught using this method is negative 3120.8. And so how does that compare? That's the multi-step reaction. How does that compare with the single step? Negative 3120.8. So you can see Hess's law holds up, that whenever we set up reactions this way, is we end up with the same enthalpy change, whether we go through multiple steps or whether we go through single steps. And right now this seems like a little overkill, because here we already knew what delta H was. But we'll look at some cases where you don't know what delta H is for a single step reaction, but you do know what it is for several smaller reactions that you could add up to make the total. So let's take a look at some more of those. So sometimes when we're applying Hess's law, it's necessary to reverse a reaction in the multi-step reaction. Recall that we said that if you have a reaction with a certain enthalpy change, reversing that direction changes the reaction from being exothermic to endothermic and vice versa, and changes the sign on the delta H naught. And so that's another technique that you can use to make these balance out if the reactions you have don't really work. So let's take a look at one here. So here we have 2C plus O2 yields 2CO, and we want to know what is delta H naught for this. But we do know that this can be written in two steps. C plus O2 yields CO2, 2CO plus O2 yields 2CO2, and we know the enthalpy changes for these two right here. And so let's see if we can figure out what delta H naught is for our single step reaction. So first thing, in the single step we want to start with two carbons, and so looking at our two multi-step one, their carbon only shows up by itself just in step one. So we want to put that in here, but because the fact the single step has a 2 out front, we're going to have to multiply step 1 by 2. And so that means it'll be, instead of being C plus O2, we're going to say 2C plus 2O2 yields, in this case, not CO2, but 2CO2. Now that of course changes what our delta H naught is. Originally it was negative 393.5, but in this case, since we're going to multiply it by 2, it's going to turn into negative 787, because that's 393.5 times 2. All right, so we have our first one here. Now let's look at what we want to get rid of. Now over on the right side we have CO2 on our new guy here. We don't want CO2, we want carbon monoxide, CO. So to cancel out our CO2, we want to react away that CO2. We want CO2 to be the reactant, not the product on our next step. But looking at our two multi-steps, there is no CO2 on the reactant side here. There is no CO2 on the reactant side here. The only CO2s show up are on the product side over here. Now there is CO2 on both product sides, so what we're going to have to do is we're going to have to reverse one of these reactions. Now, since there is CO2 on both sides, how do we know which one to use? Well, we already used step 1. That reaction is done with at this point, so we're going to have to use step 2. So let's take step 2, but let's write it backwards. Let's reverse the reaction. So we want to cancel 2CO2, so we want to have a 2CO2 on this side. Unfortunately, this already starts with a 2, so that works out pretty well. So no need to multiply this one. So we're just going to start with 2CO2. And then reversing it yields, going back this way, so now our arrow goes this direction, 2CO plus O2. All right, and now doing this, our delta H naught originally was negative 566, but since we flipped the direction on the sign, on the reaction, it's going to switch from being the original exothermic now to an endothermic reaction, and it'll be positive 566 kilojoules per mole. So let's look and see what cancels out here. So in the original reaction, we said 2C plus O2 yielded 2CO2, but we reacted and got rid of that 2CO2 over here. So now that 2CO2 is gone. Furthermore, let's look at is there anything else that cancels out? Well, originally we had two O2s, but according to this that's going to cancel out by this O2 that's over here. Not all of it, but it's going to cancel some of it. So that O2 is going to cancel out the 2 on this, because originally we had two O2s, now we've gotten rid of one of them, so we just have one. And so let's look at what remains. So now everything else is uncancelable. So we have 2 carbons plus, the only other thing here is this oxygen, so O2 yields on this other side, that's canceled out, so all we have here is just this 2CO, because the oxygen is canceled out as well. So how does this compare with the original one? 2C plus O2 yields 2CO, 2C plus O2 yields 2CO. Hey, we've managed to put together these two multi-steps to end up with the one step. Now, last step is, of course, finding our delta H. All we have to do is add them up. Negative 787 plus 566, and so when we do that, we get delta H naught is equal to negative 221 kilojoules per mole. And so that's going to be our standard reaction enthalpy for this single step reaction right here. And so we can see it's an exothermic reaction. We didn't know that to start with here, but we've been able to figure it out based on using Hess's law. So our next situation, we're trying to find delta H naught for this reaction right here, CS plus 2H2 yields CH4. And so we have 3 steps in here and a list of the enthalpy changes for each one. So we want to start off with this carbon right here. I said CS, but it's carbon solid, so it's just carbon here. So let's start off with that guy here. So we have carbon plus O2 yields CO2 right here. All right, so we have that written out. Now we have a CO2 is the product here. We don't want to have that CO2. Is that what we want to deal with first? So let's see. Do we have a CO2 anywhere else? So look at the second and third reaction steps. No CO2 on the reactant side here. No CO2 on the reactant side here, but there is a CO2 on the reactant side over here. So this is one of these where, once again, we're going to want to reverse our reaction. And so we want to get rid of one CO2. We want to react that. So let's write this reaction, but in reverse. So we'll say CO2 plus 2H2O yields, going back this way, CH4 plus 2O2. All right, we got those down. Let's go ahead and write our enthalpy changes while we've got them out here. So for this first one, we didn't change this reaction, so delta H naught is just going to be negative 393.5. For our second one, delta H naught, so we did change the direction of the reaction. We reversed it for this guy down here, and so it's going to be positive 890.3 kilojoules. So we've got that worked out. Well, let's see what cancels when we did this here. So we know the CO2 is going to cancel out over here. Does anything else? Well, we have an O2 up here and a 2O2 over here. So this is going to cancel this O2 and it's going to cancel the 2 off right there. Other than that, that seems to be it as far as we've got here. Now we've got a couple more little problems. We've got this H2O we need to get rid of, and we've got the CH4s we want. So we want to keep that there. We want to cancel off this H2O. Well, the only other reaction, so we've already done that one, we've already done that one. We only got this one left. So do we see H2O there? Yeah, here's H2O right here. So this is another one where we're going to have to, actually no, we don't want to reverse this because we want to, since it's on the reactant side, we want to cancel it by putting it on the product side. So we're just going to write this one out. Now that's 2H2O. This has got a 2 out here, so they already balance out. So let's just go ahead and start writing this guy out here. So we have our last one, 2H2 plus O2 yields 2H2O. We're just writing the regular equation, no changes to it. So that means that our delta H naught should be just what it was before, negative 571. 71.6 kilojoules per mole. And let's see what we have canceled off here. So to start with, we had this 2H2O is going to get canceled by that 2H2O right here. And well, that's sort of, let's see, what else are we missing here? That looks like that. Nope, there's one more. That's one more here. Okay, so we never canceled that O2. We just canceled the 2 in front of it. But we have an O2 down here. So that O2 is going to cancel the rest of that oxygen right there because that'll cancel that out. So now let's take a look what we got left over here. So now that we're done on this, let's write this out. So on the reactant side, we have a C right here. O2 is gone, CO2 is gone, H2O is gone. We have 2 H2s. So 2H2 like this, the O2 is gone. So now we're on the product side. We have a CH4, which is from right here. These O2s are gone, that H2O is gone, so that should be it. So C plus 2H2 yields CH4. C plus 2H2 yields CH4. So that worked out. So all we have to do to find our enthalpy change right here, our heat of reaction, is going to just add up our parts. So it's going to be negative 393.5 plus positive 890.3 plus negative 571.6. And when I do this, I get negative 74.8 kilojoules per mole. So once again, we get an exothermic reaction here, but not too exothermic, just barely exothermic. Then that's another example of how we might go about using Hess's law. One final Hess's law example. So we want to determine delta H naught for NO plus O yields NO2. So nitrogen monoxide plus monatomic oxygen. Don't see it very often, but it is showing up here. Yields NO2, and so that's what we want to find. And we have our 3 steps right here. And so we're starting off with, in our original reaction with NO, nitrogen monoxide, and step 1 has nitrogen monoxide. So let's start off with that one. So NO plus O3. Ozone is what that's called, just FYI. So yields NO2 plus O2. So our enthalpy change for this one, our delta H naught, is going to be equal to negative 198.9. We didn't make any changes here, so that should work out here. All right, so let's look at what we want to have next here. So we've got this O3, this ozone right here. Let's try to get rid of that. So because of the fact it starts off on the reactants, let's shift it over to the product side, cancel it off that way. And so to do that, we're going to need an O3 on the right side. And so O3 only shows up one other place. It shows up in step 2. So we've already done step 1. Step 2 we could do by reversing it. And so if we were to flip this back the other direction, then we would have 3O2 over here yields 2O3, like that. Now the process of doing that, of course, does change our delta H naught because we shifted the direction of the reaction. So originally it was negative 284.6, and so in this case, because we shifted the reaction on this, it's going to be positive 284.6. All right, so positive 284.6. So 284.6. Now let's take a look. Does that cancel out? Ooh, we have a little bit of a problem. If you look at what we did here, we have an O3 over here, but it's 2 O3. And this is only 1 O3. Now, normally we'd say, oh, that 1 O3 just cancels one of this 2, but leaves an O3 behind. But if you look at our last reaction, we've already at this point used 2 of them. Our last reaction has no O3s involved. We can't separate this out and eliminate it. So what we're going to have to do is we're going to have to go back to this first equation right here, and we're going to add some coefficients to it so that we can cancel out that O3. So remember here we said, hey, we're not multiplying that by 2. Well, we're going to have to go back and multiply it by 2. And I'll show you why. Watch what happens here. So if I multiply this by 2, that becomes 2NO. That becomes 2O3. That becomes 2NO2, and this becomes 2O2. Now, in the process of doing that, that now means that this is no longer negative 198.9. This is now going to be twice that. It's going to be negative 397.8 because we multiplied it by 2. But by doing this, this lets us cancel out these ozones, those 2O3s that we had right there. That's going to be important because otherwise we cannot cancel them out. And so sometimes you have to do this. You know, in the past what we've done is that we've said, like, on equation 2 we've had to double it. But it's possible you could actually have one set up and realize, oh wait, I've got to double equation 1, step 1 in my reaction. That's perfectly fine. There's no problem with doing it that way. Now let's see what else cancels on here. So we also have a 3O2 over here and a 2O2 over here. So we can cancel out the 2O2 by canceling out the 3 on this side. We still have an O2 that's on that side. So right now we have 2NO plus O2 yields 2NO2. And so right now we still have an O2 on this side here that we don't want. We're going to want to get rid of that. We're going to want to shift it away. And so to do that, we've got only step 3, the only last step remaining here. So because we want to get rid of that O2, we're going to have to put the O2 over on the O2 needs to be over on the reactant side here. So we're going to have to reverse this reaction so that then we have on this side 2O yields O2. Now, does this work out? Well, we already canceled the 3 on this one, so that should be fine in terms of doing this. And so let's see what that does. So that's in the reverse order. So because of the fact that we had to reverse this, that means that our delta H for this, delta H naught, is going to be not 495, but it'll be negative 495.0 kilojoules per mole. So once we've got that set up, let's see what it cancels now. So the process of canceling this, we had the O2 is now gone, that O2 is now gone. So all we have left here is the 2NO, the 2O, and the 2NO2. So let's add these up, see what we get out of this. So when we do this, we get 2NO plus 2O yields 2NO2. So is that the original equation? 2NO plus 2O. Oh, the original is just NO plus O, and this other one is 2NO2 versus that one's NO2. Well, look at that last equation here. It's the same as the original one, but it's not reduced. It's doubled. So when we add up our delta H naughts, we can add these up, the negative 397.8 and the 284 and the 495.0. And we do this, I end up getting that delta H naught for the whole thing is going to be negative 608.2. But that delta H is for this sort of doubled reaction. We don't want the doubled reaction. So we're going to do the same thing we've done in the past where we've had to double a reaction and that double delta H naught in reverse, because we don't want this reaction, we want half of this reaction, where instead of being 2NO, it's just NO, and instead of 2O, it's just O, and instead of 2NO2, it's just NO2, because that reaction right there is the same as this reaction right up here. And so to do that, though, we divide it all by 2, so delta H naught is also going to be divided by 2. So we'll take the 608.2 divided by 2, and we get negative 304.1 kilojoules per mole, and that is going to be our final heat of reaction for this NO plus O yields NO2 reaction.